Chemistry, chemistry, organic chemistry with Aja. Bump.
Hello everybody and welcome to Organic Chemistry with Aja James. Today we're going to be talking about the synthesis of lidocaine. Ding 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 ding. Lidocaine. Here is the structure of lidocaine. So what had happened is it's a two-step synthesis. The first one being an acylation of 2,6-dimethyl-aniline with chloroacetyl chloride, and the second step is an SN2 replacement, which is a displacement of N26-dimethylphenyl chloroacetamide with diethyl to anamine. Wait a second, haha, a diethylamine to lidocaine freebase. Woo, 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 what a mouthful. But let me tell you, this mouthful is really, really, really important. It is a type of local anesthetic that many doctors and patients and people use today. I've actually used it on other patients before when they have inflammatory spots on their body to help soothe and numb the area to relieve pain. The aniline nitrogen lone pair electrons act as the nucleophile and add into the carbonyl carbon of the acid chloride. This CsP2 trigonal planar carbon atom is incredibly electrophilic. This is due to the electronegativity of the oxygen and the chlorine carbons that pull the electron densities towards itself. And after the nitrogen-carbon bond forms, the pi bond breaks into the lone pair of electrons, and a tetrahedral intermediate is formed. An intermolecular proton transfer happens, and then the tetrahedral intermediate collapses, and the carbon-oxygen double bond reforms with the loss of a chloride anion to produce the protonated amine. Lastly, deprotonation of the protonated amide gives a secondary amide product that participates out. The acetate anion is added to help buffer the solution, act as a base in the acid-base reaction, and also decrease the solubility of the amide product. So, to start off with the synthesis of lidocaine, in the first part of synthesizing lidocaine, we took 248 microliters of 2,6-dimethyl-aniline, mixed that with 2 milliliters of glycolic acetic acid, and 175 microliters of chloroacetyl chloride. We took those things, mixed them in a flask, swirled it around, and then we heated it up precisely. After that, we added about 600 milligrams of sodium acetate, and when that was added, a white cloudy solution was formed. Then we proceeded to cool it in an ice bath, and then once that was done, we took it out, put it through a vacuum filtration apparatus. Once we collected the white solid into a tarred aluminum dish, we left that for a week so it can finish drying. And the next part of the experiment is step 2 to synthesizing lidocaine. The second part in synthesizing lidocaine is the substitution of N26-dimethylphenyl chloroacetamide with diethylamine. A substitution reaction completes the synthetic sequence of lidocaine. So, the SN2 displacement of the chloride ion from N26-dimethylphenyl chloroacetamide by dimethylamine yields, just kidding, lidocaine hydrochloride. The N26-dimethylphenyl chloroacetamide from part 1, the crude product we got, is the primary alkali chloride electrophile, and the dimethylamine is the neutral nucleophile. Because this is an SN2 reaction, the reaction is consecrated, which means that the bond making and the bond breaking happens at the same time. So the nucleophile attacks the primary alkali chloride from the backside to the leaving group, which is the chloride ion. As the bond forms, the carbon-chlorine bond breaks. The diethylamine is not the strongest nucleophile, and the toluene is not a polar aprotic solvent that will stabilize the transition state. But regardless, the reaction is going to happen with a lot of heating. The diethylammonium chloride is the byproduct of the SN2 reaction. And an excess of diethylamine is necessary because after one molecule acts as the nucleophile, the second will act as a base. A fast acid-base reaction makes sure that the lidocaine hydrochloride and diethylamine will give the lidocaine freebase and the diethylammonium chloride in equilibrium. The lidocaine freebase is the wanted product, and so a liquid-to-liquid extraction with the proper acid and base considerations is necessary. So before starting off with the second steps in synthesizing lidocaine, we need to calculate the molar equiv because it is a 5-to-1 ratio. So we start out with the mass that we get from our crude product that was left to dry from week 1. We multiply that by its molecular weight and we get the amount of moles. From there we multiply it by 5 because, like we said, it's a 5-to-1 ratio. So we get the new number of moles that we need. From here we multiply the amount of moles by its molecular weight, and this gives you the amount in milligrams. So then we multiply the density of the diethylamine and we get the wanted amount of microliters. So in this part, we take our crude product that we get, add the calculated amount of diethylamine, and about 5 milliliters of toluene, and then we reflux for 90 minutes. This process is pretty long, so I worked on my worksheet. Or we can do a little dance break. Once the refluxing is done, what we want to do is transfer that liquid into a clean culture tube, and then we will rinse it with N-hexane. And now it brings us to the liquid-to-liquid extraction. So, in the liquid-to-liquid extraction, we are going to take HCl, which is our acid, and mix it in about 2 milliliters of it into a culture tube. Then we're going to swish it around gently to see the 2 layers form equally-ish, kind of, not really. The organic layer is going to be on the top, and the aqueous layer is going to be on the bottom. The purpose of the hydrogen chloride is to help us differentiate between the 2 layers, the organic and the aqueous. The HCl forms with the lidocaine to create a lidocaine hydrochloric salt, which is more soluble in water, which would be in the bottom aqueous layer, and then the lidocaine free base, which is what we want, the amine, is going to be found in the organic layer. Solubility! Woo-woo! Once the liquid-to-liquid extraction is done 2 times, we place it in an ice bath and add KOH dropwise to the solution. This is a very basic compound, and we taste the basicness of the solution on a piece of pH paper. The purpose of this is to help freebase the lidocaine hydrochloric acid compound. After a sufficient amount of cooling, we then vacuum filtrate the crystals to collect the solid. But unfortunately, I did not get any crystals to collect. But that's okay. It wouldn't be lab without sources of errors, right? Due to me not having any crystals, it's very probable that the organic phase was accidentally transferred into the culture tube of the aqueous solution. The free base would have been dissolved in this very small layer on the top of the culture tube, and therefore the solution would be to leave it to dry throughout the next course of the week. That's all the time we have for this week's Orgo experiment. Unfortunately, we cannot see what kind of products we get left over, but if you subscribe to my channel today and follow me on social media, we'll be sure to post and update all about the product that we get. So do that.